方便放哪里？
就放这儿吧。Hello， 可以导航。要录音对吗？
不用离太近。
不用离太近是吗？好。
对，因为如果你没有口袋，
那我就站着，不要走太远，我这样应该可以。没关系。要开始吗？
Okay, so welcome back. Our next speaker is Professor Zhang from Zhejiang University. She received her PhD in computer science from Stony Brook University and PhD in mathematics from Zhejiang University. Before she came back to Zhejiang University, she worked at Harvard University. So today she's going to talk about unveiling hidden backdoors in manifold distribution gaps. So let's welcome.
Thank you for the introduction of me, and I am very honored to be here again to have this plenary talk, and very gratitude for all the organizers to inviting me. And very lucky, last year I had the chance to attending this conference, and I met Professor Adi Shamir, and so we talk about some research about the security. So he introduced me concept of the model stealthiness. So today my work I will presenting today was inspired by this conversation. This is my first research related to the security. So so at the beginning, I may give some like background knowledge about the backdoor attacking, this kind of stuff. So firstly, I will just very brief introduce about our work, our model. So the tree model assumes that the attack has access to publicly accessible and trusted clean model specified by the user, and the complete training data set used to train the model. The backdoor is implanted during the fine-tune stage of the clean model, but can only modify the final layer of the model. So the objective of the backdoor is to cause the victim model to assign correct labels to clean input and a specific target label to poison input. So the poison samples should be subtle enough to evade human detection and several backdoor defense methods. So we can see the figure in the right is the schematic diagram of our model. So we can see the pupil encode part is not editable. We can only edit the red layers, which is usually the last layers. And also, the clean samples and these poison samples should be very, very similar. Then the samples, the poison samples not only escape the human inspection, but also can pass the certain defense methods developed by methods for these backdoor attacks. So at the beginning, I will give some background introduction about this kind of the attacks. So firstly, we will introduce what is the backdoor attacks in case some of you will still not know, but it's very basic background knowledge. So the deep neural network has gained tremendous popularity as a powerful tool in various domains, such as the computer vision, the speech recognition, due to its flexible structure and remarkable performance. But nevertheless, the DNN has suspected adverse attack that create poison samples during the test phase, or backdoor attacks that create poison samples during the training phase. So starting backdoor attacks evaluates the robustness of neural network. Research on such attack can facilitate the development of effective defense mechanism, enhance the model design and the training strategies, and rectify vulnerability within the models. So we can see the two figures on the right. So the figure 1.1 is like the adversary talk, which is aiding incredible perturbation in at the inference time to alter the decision, we can see when we add this very small computation, the panda will be recognized as given. And the figure 1.2 is the backdoor attack, like which we want to introduce today. So the benign, for these backdoor models, the benign sample receives the benign behavior, but if you put the point in the sample, then it will receive the malicious behavior. So there is two types of the backdoor attack. So the first attack, we can see the line above. So the first attack, it triggers to the benign dataset to construct a poisoned dataset, which is this yellow dataset with the red triggers, and upload it to the cloud server. So the first user will download the dataset and train this own model with it, then which end up with a backdoor model. And the first attacker could add trigger to any banana sample to attack the first user's model. And the second one, the second attack train a backdoor model with a poison sample generator and upload the backdoor model. The second user may not afford to train a model from scratch, so he would download the model from the server and use it directly. However, the attack two can generate poison samples and with his generator and attack second user's model very easily. So this is the two types of the backdoor attacks. So firstly, let me introduce the data poisoning. So the backdoor images are formed by adding triggers to clean image. We can see the figure here. And these triggered image are mixed into the data set. And the user may unintentionally download the compromised data set from the internet for this model training. And upon encountering the trigger data, the infiltrated model behaves maliciously, despite exhibiting normal behavior when processing benign data. So we can see the figure here. So we can see if it's the benign data, when the benign data goes through the victim model, the car will be recognized to the car. And if we put the trigger on this car, when this image goes through this victim model, then it will be recognized to airplane, and also the truck the same way. If the image do not have any triggers, he will be recognized as a truck correctly. But if we add the triggers on this image, then when this image passes victim model, it will all the images with the triggers will be recognized as an airplane. So this is the different triggers developed by previous researchers. So this kind of but we can see the trends of these triggers from the left to right. So we can see the point in the image from each backdoor method. The trend is the data poisoning attack is to develop more like the stealther. Like we cannot find this, like the last one is more like the original one. We cannot find the triggers on the image, but like the previous one, it still have a lot of like the obvious triggers. We can recognize it. So that's the more specific introduction about this model poisoning. So the attacker creates the poison samples using a generator, and the combined set of generated poison images and the clean images is then implied the model training, and the optimization of both the generator and the model is executed with the malicious objective. So the manipulated model is unveiled to the user, and the malicious response emerge when the attacker utilize the generator to create this poison samples. So here is the process. So we have clean imager. We generated the poison data, and we train the clean imager and the poison image together and get the models. And when we use this model, so if user using the clean imager, they pass these models, then we get the benign answers. And if we generate image with the triggers, then we get all the pass this model and we get malicious answers. So let's see. Before our work, I will see that there are some limitations for this kind of previous backdoor attack methods. The first one is the explainability. We know that the explainability is crucial for the DNNs and their related work in several aspects, such as the high reliability requirement, aesthetic and large requirements, and scientific usage. So previous studies utilize the encoder of classifier models to map trigger samples to the latent space, and that kind of approach operates in black box manner, so obscuring the precise location of triggered samples within the latent space, their position relative to the manifold, and their relationship to the clean samples. We all don't know that. So consequently, it lacks of the explainability. And another issue, which we will emphasize today, is the model stealthiness. So the model stealthiness is a newly developed significant factor in evaluating the stealthiness of backdoor attacks. So it measures the number of weights used in the backdoor within the models. So previous studies require like significant amount of attackable weights for optimization to establish the connection between the trigger and the target label. So this could raise suspicions as more companies and researchers become aware of the existence of the backdoor attacks. So this is like the overview of the proposed method we want to use today. So firstly, unveiling the nature backdoors. Because the whole idea is we need to unveiling the nature backdoors between the manifold distribution gaps. So these features are of manifold, but are also closely related to the attack target class. And the backdoor model training would only influence the final layer of the classifier, which, as I said before, hence improve the model stealthiness. So we only added to the a classifier header, which is usually is the last layer. And the triggered image generation with trained generator to produce sample-specific triggers, which is more difficult to expose because for each image we have a very specific triggers. So it will be very hard to find by the human or find by the defense method. So in this work, we focus on the identifying like specific features for the backdoor features instead of relying the black box encoder. So this work is wholly like inspired by the model mixture phenomenon. So we can see can see the figure here. So there are three modes or three classes, like the triangle, the dot, and the square. So in the latent space, we can see the red dots. We use red dots are model mixture features, and they are located by our OT method from mapping singular sets in this noise space Y. So these ambiguous samples have features that typically fall into the gap between the manifold distributions and are closely related to the mode they are mixing with the Euclidean distance. So So this means if this feature is mixing model, triangle, and square, so it possesses characteristics of a square when simultaneously having a high potential to be classified as a triangle and vice versa. So this phenomenon resembles a very nature backdoors hidden between this manifold distribution. So by identifying those model mixture features around the attack classes, like this attack class is triangle in our case. So this allows us to refine the classifier head, which is the final layer of the model, to expand its decision boundary for the attack target class, thereby increasing the likelihood of backdoor features, which is the red dot here, and being classified as an attack target. This approach enhances the model's stealthiness by altering only one layer of the clean model. So we can see here, we have M1 dots, M2. They are all the model mixture points, but the M1 is more close to other modes, but the M2 is more close to the target modes. So we're using the M1 to extend the boundary of this target modes. Then we know that M2 will be included in the target, but they are like in the mixture part. It's not belongs to any mode of this any mode for the different mode. Then we using this trigger. We generating this. We using the generator to generate the perturbation and to make the clean sample more close to this M2, and then we're using this image as our triggered image, and we can using this model and the whole model, the model for the backdoor attacks. Okay, so next step we will introduce the method to how to calculating this kind of the model mixture triggers. So before we introduce our algorithm, I will introduce the understanding of the deep learning and the understanding of the deep learning in classification. So here we have a manifold hypothesis. So in high-dimensional background space, the real data distribution of a specific class is close to how-dimensional manifold, in a low-dimensional manifold. So if we have a lot of face images, then this all face image will create the manifold for the face manifold. Okay, so the clustering distribution, so the distance among the part, we know we have the distributions on this manifold, so the distance among this probability distribution of the subclass on the manifold are far enough to discriminate them. That's how we classify the different subclass on this manifold. So based on this concept and understanding, we can see the main task of deep learning can be divided by two. Firstly, we need to learn the structure of the manifold, and then we need to learn the probability distribution on the manifold. Okay, then let me introduce how we're thinking about the cause of the model mixture. The model mixture phenomenon would exist, I think everyone knows. So as pointed out by these previous researchers, the optimal transport map that push forward the Gaussian noise distribution to generate distribution may be discontinuous when there are multiple modes in the data distribution. However, as a common expression of the generator of GAN or the decoder of the VAE, the neural network could only represent continuous mappings. So this conflict raises model caps and model mixture issues. So we can see these two figures. Oops, sorry. Okay, we can see the figures. The first figure is the samples from the noise space Y, which the backdoors are all mapped to the black doors in latent space Z, so which is the model caps, because he cannot generate any other modes, like he cannot generate the square or triangles. And the second line is the model mix, the illustration for the model mixture. So the samples from the Y, which is the red dots, are mapped to the red dots in the Z, and this kind of red dots is model mixture features. So the main confliction here is like this deep neural network can only approximate continuous mappings, whereas the transform mapping are discontinuous mapping with like breakpoints. So in other words, so during the whole GAN training process, the target mapping is not within the representation function space of this DNNs. So this obverse contradiction leads to the convergence difficulties. So if a support of the target probability measure has multiple connected branches and the GAN training results in continuous mapping, it is possible that the range of the continuous mapping is concentrated in one of the connected branches, which is known as the model caps. And if continuous mapping is forced to cover all the connected branches, then the range of this continuous mapping will cover the region, will cover some regions like outside the images. So we will generate some meaningless images here. Okay, so here is the figures. The figure 2.5, it generated model mixture images by this kind of a popular data set like CIFAR 10, 10 ImageNet, and the GISTER. So the figure 20.6 is also the model mixture samples generated by the normal neural network, and it's from the PubFig. So we can see these figures have the mixture modes. So although we know that the model mixture features originate from this generative model like the GAN, the VAE, they cannot, but we still cannot effectively obtain using these models due to the lack of the control. So therefore, we use the optimal transport to compute the transport map between this Gaussian noise distribution and the manifold distribution, enabling us to locate the model mixture features. So now let's introduce how to compute this optimal transport map. So firstly, let me define this OT pattern. So it's a Monchian pattern. So assume X, Y are subset of D-dimensional Euclidean space, and the mu and the nu are probability measure defined on X and Y respectively, and C is the cost function representing the cost of transporting a unit mass from X to Y. So Monchian's problem is to find a mapping T that minimizes the total transport cost. So actually, also this problem is called optimal transport problems. So here we will introduce our like semi-discrete how we discretize this OT map. So the semi-discrete OT map, the distribution transformation to push forward to continuous south measure mu to a direct measure nu. So that's representing a semi-discrete OT map. Assume continuous south measure mu is defined on the convex domain sigma, and the target direct measure nu is defined on the discrete set Y. So the direct measure has the same total mass with the source measure. So the measure preserving semi-discrete transport map induce a cell decomposition on source domain. We can see the figures here. So the figure 20.5, the semi-discrete OT map induces the cell decomposition. So all the X in this WI, the cell WI in source domain is mapped to the YI, which is the latent feature in the manifold distribution. So the cost function C stands for the cost for transporting a unique mass from the source to target, and is given by the C and the semi-discrete form of the total cost. It's defined as follows. And we can see the semi-discrete OT map is given by this T star. But as we said, the OT map is not continuous, so we cannot calculate the OT map directly. So here is the Brunner theorem. So suppose X and Y and the Euclidean space and the transport cost is quadratic Euclidean distance C. So furthermore, if mu is absolutely continuous and mu have finite second order moments, then the existence of a convex function U known as the Brunner potential. So the Green map lambda U provides the solution to the Munchen's problem. So the Brunner potential is unique up to a constant. So when if we want to solve this Munchen's problem, so we to calculate OT map, actually we will calculate the gradient map lambda U, which is the gradient of the Brunner potential. It's continuous. So here is the discrete definition for this Brunner theorem. So by generalizing the Brunner theorem to discrete target measure, we obtain discrete Brunner theorem. Assume that mu is a source measure defined on the convex domain sigma, and the target measure is mu is in a direct measure, and with the same total mass with source measure, the discrete Brunner potential is a piecewise linear function as this, and the projection of this Brunner potential induce the cell composition here, Wi. So we're calculating the H here. So here is how we calculate. For any V2Vn, there exists H. I just said it's the calculating H. Unique up to adding the constant C to this WIH equals to VI. So for all the I, the vector H is unique minimal argument of the following convex energy EH here. So then we can just calculating actually it's just adjust the H, then makes the energy like equal. So this semi-discrete OT map, each sample with the Gaussian noise distribution to manifold distribution without generating any suspicious samples lie in the gap between manifold distribution. So the piecewise linear extension of the OT map is introduced, and it estimates the mu mass centers of each cell in source domain sigma, and the Poincare of this cell decomposition induces the triangulation of those centers. So by interpolating latent codes according to the triangulation, the OT map is extended, and this can generate new samples we need. So here is how we generate the model mixture samples. So the projection of the Brunner potential divides the source domain sigma into the multiple cell with the samples and each cell mapped to the corresponding target. The mu mass center C1 is estimated to calculating the mean value of all samples in the WI. And the point west mapping from the C1 to CI to YI is constructed in the way using the T tilde. And the vertices of the cohesion surrounding the X are determined as the nearest D+1 mu mass center CRK in the Euclidean space. So X is a random sample from a Gaussian noise distribution. So the extended OT, like T tilde, map the X into the Y, the T tilde X here. So it's we calculate the T tilde I using the Y1 to YI, using the importation. Okay. So that's how we find the model mixture location. So with the extended OT map T tilde, different vertices of some cohesion may belong to different modes, and interpolating new samples with those vertices will result in mode mixture phenomenon, generating features that typically lies between the manifold distribution gaps. Locating those mode mixture feature is known as the singular set detection. So for giving Gaussian noise sample X, it is possible to tell if it belongs to the singular set by examining the angle theta. So between the hyperplanes, if all the angles exceed a given threshold, X belongs to the singular set. So we can see the red line here. Actually, it is the ridge on the Brunner potential. So its projection onto the omega will from a singular set, which is the red line. So here is the domain omega here, right? The omega in the domain omega, then the xi is here around this ridge, and this ridge actually is the singular set from how we find these mixture features. If there's samples inside this singular set, the xi, it will be mapped to the feature that locate with the manifold distribution gaps. We can see the right figures. So these two, the yellow line, they form the two different kind of the modes. And if we using the T tilde from xi to the T tilde xl, the point here, it will be located in the gap of these two manifold. So here is our the backdoor model here. So a classification mode can divide into the encoder theta E and a classifier theta C. The encoder operates the manifold embedding, while the classifier had classify latent codes into the corresponding classes. So the object of the classification mode is described as a C star. So D is the data set, and L is the loss function, and theta is combination of the theta E and the theta C. So only the theta C, our model is only added to the theta C. Okay, then we can introduce the backdoor model we have. So a feature dataset DF is initially created by applying the theta E, which is this pupil part, and in the training set, then the point and the features dataset we call the DFP is constructed, and during the construction of the DFP, mode mixture features further to the attack target class and closer to other classes. And we denote here as M1 are implanted into DF and labeled as belonging to attack target class. So this is accomplished by manually turning lambda k in extended OT map X for those X belonging to the singular set. So this theta epsilon is then refined on DFP as follows. So I think I introduced the whole idea in the previous slides. So here is the last how we modify the theta C, the last layer. So by refining the theta C over the DFP, the decision region of the attack target class will extend towards the manifold distribution gaps, and contain some original of manifold mode mixture features that is not as far from attack target class as M1, so denote as M2 when converting a clean sample into a triggered sample that cause misclassification. Generators are applied to generator perturbation to push clean sample towards M2 in the latent space, since the C2C is commonly selected as the final layer of the classifier. Only one layer of the clean model has to alter to implant the backdoors. So actually we can see the figures, we're using the M1 as a boundary of the target modes. So the M2 will be included in we will be included as this target modes. So then we use this kind of the samples as the trigger samples and train the C. So here's how we craft how to crafting or pointed samples. So the crafting pointed samples involves aiding perturbation to clean samples so that they approximate M2 in the latent space. The transform function is described as TR as followed, and the G is a generator that generates sample-specific triggers, and the optimization of G is described as follows. So, here, every trigger, like the different image, actually have different perturbations. They are very specific by images, so it will be very hard to be detected. So here is the whole model. So we can see we intend to our intention is to explore the certain features as the backdoor features, and we find this kind of model mixture features are suitable since they are between manifold distribution gaps and they have the characteristics of the one mode and are easily classified as the other mode, which is almost a nature backdoor. To unveil them, we apply the semi-discrete OT map to calculate. And the images here, the left bottom, to enhance the model's stiffness, we only need to train the classifier head, which is only one layer. To embed the backdoor, M1 are labeled as belonging to the triangles, and that's expanded to the decision boundary of this kind of triangles, and which is contains all the M2 here. And in order to generate the triggers, we apply the generator. It generates sample-specific triggers. As I said, like every image, they have different triggers. They push points and samples to M2 in the latent space. So the trigger actually is added to the benign image and puts the images to move to near to the M2 location in the latent space, and it will classify it as the triggers. It will classify it as triangles. So in the conclusion, our method is both good at the explainability and the model stiffness. So here is the experiments setup. So actually, we using our method. We're using the different data set, including the Minster, the CFAR10, the disturb, and the ParkFix, and this data set we are use. And here is the hyperparameters we use too. So we attack all the Minster data, the trigger data to the 0, and we attack all the CFAR10 image, trigger image to the airplane, and the figures, and also the different target, and also the victim model, the pre-trained model. We have several parameters. All the parameters are here. So here is the choice of the hyperparameter, like for our OT, because as I said, based on this Bernier, we're using the Bernier potential to finding this singular set, so we can control like how close to which model. Like we can choose the location in the latent space, and we can choosing different probability. Like we can use this model more close to like triangle, or more close to the dots, or more close to the square. So this is our settings. We setting the different when we train our model, all the parameters like the mu1 we set like 0.25 and to YIK from attack target class, and 0.75 to the YIK for other classes, and the M2 we set is 0.5. So all the location, the image generating location are controlled. We can control all this stuff and to generate more precise images we want. So here is our attack success rate. So for this experimental, we set our model like very small change for these parameters, but other models, they can change all the parameters. So the other changes are big. So even that, our performance is good too, not bad. Most of them achieve the SOTA. And if some of them not achieve SOTA, we're very close to it. So this is the success rate. And if we fix the other method, right? We keep the theta E of the pre-trained clean classifier fixed, and only allows the other method to optimize the last layer. So the result will be in this table 13.3, indicate that in this scenario, when user will only accept minor modification on a trusted clean model for their safety. So we can see all the other method performance probably much bad. Our performance will still keep good. So that's another experiment. Okay. So we can see the changes. So other model, when we're using attack models, adding the backdoors, they using whole parameters, change a lot of the parameters, but our weights are fixed very small. So here's effective weight is only like the 5K, very small compared to the whole weights, right? So we only modify very small number of the weights. And here is another experiment, the function of the range distribution. Like the table 35 presents the function range distribution of the altered weights. The function range is qualifies as we define as this, and using the ILE2 as a milestone. So our method displays a large segment of weights within this range, like smaller than the LE2, we change very smaller. The most of our weights, the change were very slight, very small. So this implies that our method imports only smaller weight count for backdoor embedding, but also reduce the fractation range while maintaining comparable attack accuracy. And here is our poison samples, and we can see the compared to other methods poison samples, our stealthiness is much better, but especially in the residual image, or others can find some in this, but R is very clean here. So it's our like the image we generated is more stealthy. So here is another sample stealthiness examples for our other method. We can still see the triggers, right? But our method is hard to find this image is trigger image. And another visualization for the points image from our methods. can see our method, our present image looks very similar to the original images. And also we try different kind of the defense methods, see if our attack can pass this kind of the defense method. So the first defense method is this neural claims, and it's a very popular mitigation defense, and the model qualifies the smallest perturbation required to manipulate the classification results of all images in a dataset towards a specific target label. Subsequently, an index qualifies the model's degree if the anomaly index of a model surpasses the predefined threshold. Actually, this line is important. If all the data not goes past the if the data is less than this 2.0, which means that we pass this defense method, they do not find that our attack or backdoors. They do not find our backdoors. And this is another fine pruning defense method. So the backdoor accuracy and the clean accuracy did not drop. If the drop, which means that it is backdoor attack or backdoor will be detected. So, but for this kind of two, we can see the figure 3.6 or the CFAR, the data set, they are not dropped. So, which means that I'll pass this defense method too. So here is another defense method. AMP defense method is same if it's not job, which means that our method pass the defense method. They do not detect it. I think we do a lot of defense methods, but we all pass them. This is STI-IP defense. And we can see the strings, the backdoor data, and the entropy of the backdoor data and the clean data. We can see the distribution cannot be classified. The distribution cannot be classified, which means that you cannot find the backdoor. You do not recognize our model backdoor models. Yeah. And another, I think it's another defense method. Okay, I think here is another. This is like another defense method, and so this method is structure a minimal pattern from an input image determining the model's output. So the upmask M is in part to derive a minimal pattern known as this connective pattern. So we can see the distribution. I think it's the distribution. Even the CFAR 10 is a little bit separate, but it should be the yellow one should be in the left of the right in the left of the blue one. So it's still pass. So our method still pass this defense. The last sorry. So the last defense method is the latent space realization. So still, both the clean and the point samples can classify into the same path. They can still be distant and separable in the latent space. So our method. Our method is the clean sample and the point sample are not distant in the latent space, so it still pass we pass this defense method too. So here's the conclusion. So the strengths of our method. So our study unveils the nature backdoors within the manifold distribution gaps. It has better explainability and the model stiffness than previous research. And additionally, we utilize the semi-discrete OT map and its piecewise linear extension to map the Gaussian noise distribution to manifold distribution and generate the model mix features with our control. And we also highlight the potential application of the model mixture phenomenon despite its avoidance as a mainstream practice. So our backdoor model method high accuracy in both clean and attack scenario, and with limited attackable weights and demonstrated reliance against a common developed defense mechanism. And also, our method is can use to the multiple modalities. It's ready applicable to not only the image classification, but also to point cloud, the video classification task. And we manipulated the latent space, rendering it's independent of a specific encoding network architecture and input modalities. So here's our limitation of our method. For the data set with a larger number of the classes and a small number of samples per class, so the efficacy of our approach decreased, and the average number of model mixture features mixing attack target class and other classes will be insufficient for the optimizing of the point and samples. So it affects the stiffness of the point and the samples. So, and also, our method today, the method we present here is like the R21 attack, and maybe later we will do the R2R attack later. And the limitation will be addressed in our future work, and we are trying to solve the problems. Okay, so thank you.
Okay. Thanks for your time. So, any question? So I have another question. So how is your method related to the semi-discrete OP problem?
Oh, because the main idea here is we need to find the model mixture features. And how you find this model mixture features, we're using the algorithm for the OT. And actually, we are trying to calculating the lambda u, which is the gradient of the Brunner potential. But we calculating Brunner potential equals to solve the Monson problem, which is OT map. So it's the things, the relations.
Okay.
So I was curious. So I guess one strength was you only needed to edit the final layer of the network, but I thought the other strength was the adversarial examples were taking into account the structure of the data manifolds. Would there potentially be a way to allow all the weights of the network to be edited less, and maybe it's harder to detect rather than just editing the weight? I guess then you're changing the latent space.
One?
So you said that the other poisoning attacks, they edit all the weights of the network, not just the final layer.
Yeah.
I wondered if there might be a way to adapt your method with your particular adversarial attack you've constructed on to allow maybe all the weights to be edited, but maybe less than you would need to edit the final layer.
Actually, our method, because our method is like the backdoors for our method is very natural because we're using this model mixture features, right? So this kind of images, they are there. When you generate the images, this model mixture images just are there. So we just collecting all these kind of images, right, to be our triggers. So when we use this image, I think it's the others. So we do not need to adjust all the weight, right? It's just a small number of weight. It will be enough. But for other methods, I think it's they need to link the triggers to the benign image. They need to link it, so they will have more. They need to modify the more parameters. It's hard. So that's our logic.
Okay.
Yeah.
Thank you.
Any question? So if there is no question, let's thank Professor Zhang.
Thank you.
So we'll have a 20 minutes break, and the next talk will start at 11.